Hey everyone, we are talking about radical expressions and simplifying them, and that begins chapter 11, section 1. And here we go with our vocabulary. We're going to deal with radical expressions. So, a radical expression is an expression that contains a radical, and so we can look at something like this 3x to the fourth power, or y, I don't know, times 2. This would be a radical expression because it's an expression that has a radical in it. The radicand is the portion of the radical that is, or the portion of the expression that's underneath the radical, like that. Rationalizing the denominator is a weird process. So you know what a denominator is. A denominator is the bottom part of a fraction. And so we're used to 2/3, and that makes sense in our mind, right? Because you're like, I've got a whole split into 3 parts, and that's 2 of them, 2/3. Got it. So what if I said 1 over the square root of 2? That doesn't feel really good. Like nobody's impressed with that. There's like 1 square root of 2th, you know. Also, it doesn't really present in our mind something that we can that's tangible. Pretty much dealing with radicals is going to be like that, whether they're in the denominator or the numerator, but particularly in the denominator, it is difficult to deal with, particularly when you're calculating things. So mathematicians have devised a plan of rationalizing the denominator. Is it necessary now that we have calculators that can do all of the work for us? Who knows? But we're going to learn how to do it anyway. So rationalizing the denominator requires a really fancy trick that I really think is awesome, and mathematicians use it all the time. They will come up and multiply a problem by 1. Yes, I said it, 1. So if I multiply this problem by 1, I get 1 over the square root of 2. Nothing happened. And that's exactly what I want. I don't want to change the value, but I want to change the look of the problem. So rationalizing the denominator is multiplying by a very special one. In this case, the one that I'm going to multiply by is the square root of 2 over the square root of 2. Stop for a minute. Admit to yourself that it's 1. I'm not changing a thing, but I am going to follow the laws of multiplication, right? When I multiply fractions, I multiply numerator times numerator and denominator times denominator. The square root of 2 times the square root of 2 is just 2. So what I've done is made my denominator rational. I've rationalized the denominator. And so that is the wonderful thing that we just did here. So why do we do it again? Because we're crazy and confused about life? No, 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 my friends. We do this to make computation easier. Oftentimes it makes computation easier. So I'll talk about what that means in a minute. Let me get rid of this example fraction here and zoom in a little bit so we can talk about the ones that we have here. So what we notice is that the square root of 2 is a little bit hard to think about, but when I say 2 at the bottom, you know what I mean. I've taken a whole, cut it in half, and now the square root of 2 still is a part of our problem, but it kind of makes a little bit more sense. Square root of 2, I can calculate it. That's 1.414. I think. So 1.414 something something. So a little bit more than half. The square root of 2 over 2 is a little bit more than half. Whereas this is a little bit harder to think about. And as I said before, easier for computation. The next phrase that we're going to talk about is, or the next word vocabulary term is conjugate. And conjugate, usually the word that I hear about after is pair. Conjugate, in terms of radicals, have a very special relationship with a radical number. So let's say I had like 2 minus the square root of 2. This is radical. This is a radical expression. This expression that has a radical in it. 2 minus the square root of 2 is a radical. So I can multiply this value by a special value that's going to make sure that I get a rational number. And that's what the conjugate does. The conjugate is kind of like the lowest number that I can multiply this number by in order to get a rational number. Remember, rational number is a number I can write as a fractions. These guys are irrational because they got radicals. So rationalizing the denominator, I want to make the denominator rational, right? All of the words coming together. So what a conjugate looks like is I really literally change this to 2 plus the square root of 2. And those are conjugate pairs. So if I had 1 minus the square root of 7, the conjugate will be 1 plus the square root of 7. If I had 7 plus the square root of 5, the conjugate would be 7 minus the square root of 5. And the beautiful thing that we're playing off of, and this you guys, you know, life is so cool. Math is pretty awesome. So remember A minus B times A plus B, and you're like, so boring. Why are we memorizing this? And we remember that it does something really cool. we lose that middle term and we just get a squared minus b squared. Well, we're kind of exploiting that when we think about the conjugate, because when I multiply these guys together, I get 4 minus square root of 2 times square root of 2, 2, right? And that comes out to 2. So notice that when I multiply two conjugates together, two conjugate radical expressions, I end up with something kind of cool, which is a rational number. And you'll see it happen again. Again, we're playing on the idea a minus b, a plus b, a squared, 1, minus b squared, minus 7 is going to give me a negative 6. Negative, but still rational. Let's do it again. A minus b, or a plus b times a minus b, is a squared. So that's 49 minus b squared minus 5, not 25. I know, I heard you. So then we end up with 30, no, I don't know. I cannot subtract because I'm talking about kids. 44. Does that make sense? 49 minus 5, 44. And so in each of those cases, the conjugate relationship is when you basically take a number and the radical portion that's being added to it, and you're going to change the sign from addition to subtraction. And the beautiful thing about that is that, you know, when you multiply it together, you get a rational number. Now that I said all that, let's go ahead and use some of these concepts in play. So one thing, and I think we probably need a couple more examples than this, but one thing is when we simplify square roots, I'm not asking you to pull out a calculator. Now we're kind of getting tough. When you simplify square roots, all you're going to do is you're going to take the, you're going to look into the number and you're going to factor it such that you have factors that are perfect squares, if you can. So when I look at 12, I know that 4 times 3 is a way of factoring 12 so that I got the perfect square of 4. This is how I do it. And you know, perfect squares are 1. 1's kind of useless in this situation, but 4, 9, 16. You get what I'm doing. 5 times 5, 25. 6 times 6, 36. It is really a good idea for you guys to memorize, and I know you don't like to memorize, down to 400 or 20 squared. The reason why is just those numbers are going to keep coming up, and it comes up a lot when we simplify. So let's go ahead. So I've taken this 12 and I've written it as 4 times the square root, 4 times 3, the square root of 4 times 3. And what I know is I can take the square root of 4. And so this is also an equivalent way of writing that. So the square root of 4 is 2, and the square root of 3, I can't simplify. So the way I simplify the square root of 12 is to write it as 2 root 3. Let's do another one. I'm going to do a bunch of these just because I think that they're necessary. So let's do 50. The number 50, I'm thinking about numbers that divide evenly into 50 that are perfect squares. And so I've got this mental Rolodex rolling around in my head. And I usually try to pick the largest one. I don't have to, but choosing the largest one will ratchet down the time that I use in simplifying. So I'm going to choose 25, and so I rewrite the radicand, the thing underneath the radical, as the product of 25 and 2, as the product of two numbers, one being a perfect square. And so the square root of 25 times the square root of 2 is another equivalent way of writing all of this. What's the square root of 25? 5. What's the square root of 2? Root 2. And so this is the exact simplified version of the square root of 50. You enjoyed it so much you want to see another one? Here's another example. So 90. I'm thinking about 90. I'm thinking that I can write it as 9 times 10 because that would be factoring it into perfect squares, or to at least one perfect square. I know that this is going to be the square root of 9 times the square root of 10. The square root of 9 is 3. The square root of 10, I cannot do. Think about it. Yep, no, can't do. And so I'm left with what we would say 3 root 10. Let's see, anything interesting. So when I multiply square roots, basically what I'm doing is I'm going to multiply radicand by radicand. I need to make sure I'm dealing with the same type of square root. Later on, we'll see that we can have little index numbers here, and that would be a no-go for us. We couldn't multiply that, and we'll talk about what those mean. But right now, there's like an understood, I'm talking about the square root, so there's like an imaginary 2 there. We'll get to that later. But since I'm dealing with the same type of radical, I can multiply these guys, and they both can get underneath the same radical. So 3 times 15 is 45. And so if I had to multiply this, I'd do that. But then I'm still thinking about simplifying my answer. And so I'm thinking, can I break this down into factors? Well, we just had 3 and 15. I know I can break it down into 3 and 15, but neither of those are perfect squares. So if I want to break it down into perfect squares, I'm going to choose 9 times 5. And so, or at least a perfect square. I keep saying perfect squares, but at least a perfect square, I'm going to do 9 times 5. And then this can be written as the square root of 9 times the square root of 5. And then I get 3 root 5. So all of these iterations of this problem are true, and this would be our final answer. Okay, so here is example 3, and example 3 has us simplifying this expression with like a whole lot going on. So what we're going to do is we're going to take our time and kind of think the way we were thinking when we were just dealing with regular numbers, right? So what we did when we had regular numbers, we looked for perfect squares that fit into it. And so I'm going to rewrite all of this thinking about perfect squares. So looking at 40, I know that's 4 times 10, because 4 is a perfect square that divides evenly into 40. It's the largest one. When I look at x to the 4th power, I'm thinking about that as x to the 2nd power raised to the 2nd power. So in a way, that is a perfect square because it's x to the 2nd power times x to the 2nd power. So I'm going to leave that alone because that is a perfect square. Y to the 5th power is not a perfect square. If I changed it, if I factored out y to the 4th power, perfect square, times y, not a perfect square. Now I factored it kind of like I did the 40 with the 4 and 10. I'm going to do the same thing with the z. I'm going to get z squared times z. And so now what I'm going to do is take things out from underneath the radical because I can take the square root of it and leave things inside which I cannot take the square root of. So if you look, the square root of 4 is 2 outside. The square root of 10 cannot be done simply, and so I'm going to do that. The square root of x to the 4th power is x squared. Take that outside. So outside, y to the 4th power. I can do that. The square root of that will be y to the 2nd power because y to the 2nd times y to the 2nd is y to the 4th. So I have y to the 2nd power on the outside. The square root of, and then so y stays indoors, right? So this guy comes out and this guy stays in. And now I need to deal with z to the 2nd power. Z to the 2nd power, the square root of that is z. I'm going to put a little thought asterisk around there. And then we have z over here as well because this z did not get to come outside. I want you to just sit there, stare at it for a second. Breathe it in. Can't wait for you to do some examples so you can kind of solidify this concept because this is an important one. Another little thing I'm going to put here, this is going to be weird. I want to talk about it though because I want to be truthful. Sometimes mathematicians, sometimes textbooks will go the extra mile and put an absolute value around this z. I'm going to explain to you why that happens. So we see z sitting here being a good person, just chilling. And we don't know if z is like a negative or positive number. But what we do know is when we take the square root of a number, the answer has got to be positive. Let me show you what I mean. You're walking down the street, you see -3. And somebody says, why don't you square yourself -3? -3 becomes 9. Then somebody says, unsquare yourself 9, and you get a +3. What happened to -3? Hun, hun, hun. The fact is, every time you take the square root of an answer, the square root of a number, you're going to get what we call like the principal square root, the positive value. We're looking at the +3 for this square root here. And so when I'm looking at this z squared, right, if I take the square root of it, it's going to be positive, right? But if z were originally negative, how do I know if it's positive? I don't know. I don't know, right? Because imagine if c were like a -8 or something like that, and I took the square root of it. When I take the square root, I don't know if I'm really going to get z back. I might get the positive version of z. So mathematicians will go through and put the absolute value here. Somebody who is an in-depth thinker is thinking, well, why didn't we put absolute values around x squared and y squared? Think about it. If x were negative, x squared would make it positive, so who cares? If y were negative, y squared would make it positive, so who cares? So we got a positive number outside. Somebody who's an extra deep thinker is thinking, but wait a minute, if we had a negative here and these were positive, then only one would be negative and we couldn't take the square root of it. And brain exploding. I know it's kind of a lot to think of, but technically like the y could be negative and the z could be negative and they kind of cancel each other out and strange things happen. I know it's a lot to think about, but I just want you to know where the absolute value comes from. I'm going to have to finish the video I'm going to have to finish this concept in the next video. So I look for you to come back soon. All right. Take care, guys.